All right, wrapping up the last little bit of Chapter 5, we learned about several types of reactions. We learned about synthesis reactions, combination reactions, where we're adding two things together, and then those were making one product. We learned about the opposite process, where we're taking one thing and breaking it up into two different things, decomposing it into multiple elements or multiple compounds. Those are decomposition reactions. We learned about single replacement reactions. And in this slide, our last slide that we did last class, we learned about double replacement or double displacement reactions, where we're swapping partners, basically. And a type of double replacement reaction is a precipitation reaction. In a precipitation reaction, two aqueous or dissolved solutions, so they're going to be clear solutions. They might be colored, but they're going to be clear solutions. You mix them together, and suddenly out of nowhere, a solid forms, and that's what this red dot pattern that I put at the bottom of this other beaker is. This red is the precipitate. So a solid that appears or is produced when you mix two aqueous dissolved solutions together. And we saw an example, multiple examples of that in one of our labs of precipitates forming. We can predict the products of single and double replacement reactions. So in a single replacement reaction, we're replacing one element. One element is getting substituted into another or with another to form a new compound. If our reactants are ionic compounds, which they usually will be for this class, then we have to choose which of those two elements is most like our lone element. Right, so our calcium in our top example is the element that is by itself. It's going to replace only one of these two elements. It's either going to replace the iron or it's going to replace the chlorine. And so we have to choose which of those two is most like our calcium. What kind of element is calcium? It's a metal. And metals tend to form positive ions. So our calcium, seeing that it's a metal, is going to replace the more metallic of these two elements in our iron 2 chloride, which is the iron. So iron, also being a metal, is going to get replaced by the calcium. Another part of this process is that we have to figure out how the calcium and the chloride are going to combine. So it may be helpful to split the iron and the chlorines, the chlorides, apart. FeCl2, chlorine always forms a 1- charge. We have two of them, so we have a total of a 2 negative charge that we need to balance with our iron. So our iron has to be iron 2+. That's why I said iron 2 chloride earlier. We'll be doing this especially in double displacement reactions coming up next. All right, so our calcium is going to replace our iron. So we'll have calcium 2+ plus Cl minus, and then all by its lonesome will be iron. Iron's going to have a neutral charge because it's by itself. And so when we recombine our calcium and our chloride, we can crisscross those. We get CaCl2, and our other product is iron by itself. The reason that iron went from a 2+ to a neutral charge is the transfer of electrons that was going on. So calcium originally no charge, gave 2 electrons to the iron, and they swapped places, in case you're wondering how the charge stuff works out. In our second example, we've got magnesium bromide. Our magnesium, normally a 2 positive charge. Our bromide, Br minus. Bromine's a halogen. It's always going to form a 1 negative charge. We've got that reacting with fluorine gas. Horse's knee oats 4, clear brown eyes, or the F in Brinkelhoff. When fluorine forms an ion, it forms F minus. It's a nonmetal. So we could maybe also see from the charges, Br minus, F minus, those 2 can swap, and we'll still be able to make a neutral compound, a neutral ionic compound with magnesium and fluorine. If we swapped the magnesium and the fluorine so that we had fluorine and bromine together, I'll show you what that looks like. If we tried to do something like this, with fluorine and bromine together, fluorine's got a negative charge, bromine's got a negative charge, we would always end up with a negatively charged compound. So that doesn't work. What does work is pairing together we'll use these little grabby hands maybe, magnesium and fluoride. So magnesium 2 plus, F minus, crisscross them, MgF2, and bromine in its normal form. And for clarity of looking at this later, I'm going to delete the wrong one. Like it never even happened. So the key for these single replacement reactions is figuring out what our lone element is most like in the compound. So if the solo element is a metal, it replaces the metal in the compound. And the same is true for nonmetal. Any questions about our selection process for that replacement? All right, the other scenario that we can have for swaps is double replacement or double displacement reactions. And you can swap either the cations, the positively charged, the metals, or the anions, the negatively charged, the nonmetals. In the slides, I'm showing it as a swap of anions. It could be an oxyanion as well. So to predict our products, we're going to separate each ionic compound. So using the example that we have below, BaCl2, we're going to separate that out. Barium is always Ba2+. Chlorine, or chloride, always Cl- as chloride. We'll worry about the balancing later. And if we have lithium sulfate, that separates into lithium, which is an alkali metal, always a 1+ charge, and sulfate, SO4 2-, which you can find in your oxyanion table on your green sheet. I'll just rewrite the separated ions out down here. So now we've got what our ions are in solution, and we want to see what new combinations can we make out of this. We could, of course, just choose to recombine them the same way, but then we haven't done anything, and so that's why we're not doing that, or not exploring that as an option. We're going to swap our negatively charged ions, our anions. So that's chloride and sulfate. So that means that our new pairs will be barium 2+, and its new partner, SO4 2-. And lithium is now paired with chloride. And then to figure out how those recombine, we can crisscross and simplify, or we can add them straight together since they are the same magnitude of charges, just opposites. So barium is a 2+, sulfate's a 2-. Those will cancel each other out. Lithium is a 1+, chloride's a 1-. Those will also cancel each other out, so we can add those together. So these would be the products in blue at the bottom. And then our last step would be that we would balance the equation. All right, let's see one in action. This is an example of something you might be given on an exam. Write a balanced reaction for the reaction that occurs when barium nitrate and potassium hydroxide are mixed. So we have to suss out what do those names mean. Barium is Ba. It'll form a 2+ charge when it forms an ion. Nitrate is NO3 with a 1- charge. Then we've got potassium hydroxide. Potassium is K. It'll form a 1+ ion. And hydroxide is OH with a 1- charge. So those are our two reactants. We need to figure out what those compounds are. In the case of our barium nitrate, we've got one subscript to crisscross. So BaNO3 with a 2 outside of the parentheses. We've got two nitrate groups. Our other reactant, potassium hydroxide, is just KOH. Questions about what we've done so far. All right, I'm going to rewrite them as separated ions. This is sort of optional because we already wrote that up above, but this is the process that I would be doing if we were given just the chemical equations, for example, on the left side. So we've broken it down into the positively charged, the negatively charged ions. We are going to swap the anions, the negatively charged ions. And I'll rewrite those below where our products are going to go on the right side. So we're kind of moving in a counterclockwise direction for the flow of solving this problem. You don't have to do it this way, that's just how I do it. So barium 2 plus is now matched up with the hydroxide after the swap, and potassium is now matched up with nitrate after the swap. To see how we recombine, we crisscross. Again, we only have one to crisscross here. It's the barium hydroxide. So we'll recombine those as our products. So Ba, OH, 2, and KNO3. And then the last step is balancing. So to balance a double replacement, double displacement reaction, we want to find something that's different on both sides. We've got two things that are different on both sides. We've got the nitrate, we've got 2 on the left, 1 on the right. We've got hydroxide, the OH, we've got 2 on the right, 1 on the left. We can start with either of those. I usually just start with the one that shows up first, moving left to right. So I'm going to start by balancing out the nitrates. We've got 2 on the reactant side, 1 on the product side. So to balance those out, we need to bump up the amount of nitrate that we have on the product side. So we'll add a coefficient of 2 in front of our potassium nitrate. When we do that, what else do we change? The potassium. So the potassium changed, we're going to balance potassium next. So we now have 2 potassiums on the product side, and we only have 1 potassium on the reactant side. To balance those out, add a 2 in front of our potassium hydroxide. Now our potassiums are balanced. When we changed the amount of potassium that we had, that also changed the amount of hydroxide that we had. So let's check our hydroxide now. We have 2 on the reactant side, and we have 2 on the product side. So that's already balanced. The last thing that we need to check is our barium. For barium, we've got 1 on the product side, 1 on the reactant side. Our barium is balanced. Very good. So this is about the most involved, not the most involved, but it's close to the most involved version of this problem that I might be able to give you. Questions about the process? Yes?
The NO and the OH, do they switch because they're negatives? Or why?
Why did we choose to switch the NO3 and the OH? Just so that we're only switching one set of things. So we want to look at, like if we could look at all the possible combinations for these 4 ions. Our positives have to match up with a negative. When we started, our barium was hooked up with nitrate, and so we swapped it over to the hydroxide, the only other option that we have to produce a neutral charge. If you want to, you can swap the positively charged ions instead. This is just a nice, easy method to make sure that we end up with new products. Any other questions? All right, one for you to try. Predict what will happen if rubidium hydroxide and cobalt-2 chloride are mixed. I'm going to change that to write a balanced reaction. And I'll give you a couple minutes to work on that. After about a minute or so, I'll write in what those compounds are. We'll go one step further, separating these out again. So after we do our anion swap, our rubidium and our chloride are together, our cobalt 2+ and our hydroxide are together. Then we crisscross. We don't have to do that for the rubidium and the chloride since they're 1-to-1. A 1 positive charge balances out a 1 negative charge. And then we can recombine. These are our new pairings. So we've got rubidium chloride and cobalt 2 hydroxide. And then our last step to do is balance. So looking at things that are not equal to find the differences game, chlorine is not equal. We've got 2 chlorines on the reactant side. We've got 1 chlorine on the product side. We need to rectify this great injustice. So we're going to bump up our rubidium chloride to 2. And when we make that change to balance out our chlorines, we have now changed our rubidium. So we're going to balance rubidium next. So Rb, we've got 2 on the right, 1 on the left. So on the reactant side, we need to increase our Rbs. So now that we've got our 2 Rbs on the reactant side, we have the meets. But what else has changed is our hydroxide. So we have 2 hydroxides now, conveniently 2 hydroxides on the product side as well. So those are already balanced. The last thing to check is our cobalts. Our cobalts are balanced. So just as a little bookkeeping, we'll write down the CO as our last group to check. Notice that I'm keeping the polyatomic ions intact. So like the hydroxide that we have in this problem, I think it was the nitrate in the previous problem, we're keeping that together as one complete unit that reduces the number of things that we have to check. Any questions about solving or predicting double replacement or single replacement reactions? Yes?
How do you check for mistakes? Like, how do you check
So to check that you balanced everything out, you could either erase your list of things as you were balancing it across, and then go through it again, just count everything up. Or you can just do that with it still there, or you could do a separate list. So like the first thing that we have on the reactant side is our rubidium. We've got 2 Rb because of the coefficient of 2. On the product side, a coefficient of 2 in front of our rubidium chloride. Rubidium is balanced. Looking at our hydroxide, on the reactant side, we also have 2 hydroxides. On the product side, we've got a subscript of 2 on our hydroxide and cobalt-2 hydroxide. So hydroxides are balanced. Next up, the cobalt. We have 1 cobalt. On the product side, we have also 1 cobalt. And then the last check is our chlorines. We've got 2 chlorines because of our subscript of 2. Our coefficient of 2 in front of rubidium chloride, RbCl, means that we also have 2 Cls. So everything's all balanced up and good to go. So depending on how confident you are in your abilities to get these right every time, you may or may not go back and double check your counts. I usually don't, but that's just because I have hubris. And that will do it for Chapter 5.